So what we're going to do here, we're really just going to talk about how you control what's going on in the code in terms of the reference state that's used and the non-dimensionalization, the boundary conditions that can be used, the initial conditions that you can select, and I'll give kind of an overview. There's three different background states in Rayleigh, and so we've got some input file examples we'll use to initiate a Boolean-esque simulation, a non-dimensional anelastic simulation, which is actually one of Maritz's Jupyter runs, and then a dimensional anelastic simulation, which is one of my solar runs. Okay. Okay, so before we begin, there's a little bit of prep work here. So the first thing we want to do is we're going to make a module 3 directory, and we're going to copy 3 different input files, and we're going to create 3 directories within it. And we're going to copy the indicated input files from input examples into those directories. So we'll start there, and then let me know if you have any issues finding the files, but they're in the Rayleigh input files, input examples directory. And then don't forget to soft link Rayleigh into each of these 3 subdirectories. Okay, these are going to be 3 different runs that we play with.
Question?
Yeah.
Where are the last 3 lines? Where are the first? Where's C2001?
Yeah, those are in Rayleigh / input examples. So that's kind of ready. Rayleigh. Did you find it? What you'll probably have to do if your machine is acting like Bruce's, you'll have to actually soft link from within each directory.
So you have to give the path all the way. You have to give it path that's coming a long way back.
Yeah. So what you'll need a command like this.
So we want to go twiddle desktop.
You could go to twiddle desktop or do two dots. Build Rayleigh dot. So this will be probably the soft linking that is sure to work. So this is by far the most complicated setup of the tutorial. Okay. I was going to make another note about name list, but just remember, don't modify what I don't tell you to modify. Okay. We've been deleting this benchmark mode, but I made a note of it here in the PowerPoint too. But basically any of the benchmark examples contain benchmark mode equals X, so that Rayleigh knows to do the analyses, the benchmark analyses. Doing those is actually kind of expensive, okay? Because there's a lot more communication going on to take global averages of things while the run is going. So that's one reason you don't want to just have that on all the time. The other reason, though, is we've already said is that it overwrites whatever inputs that you want. Okay, so you should delete benchmark mode equals X if you want to take one of the benchmark examples and modify the physics slightly. Okay, or if you just don't want to perform the benchmark analyses for whatever reason. Okay. All right. So in the boost / main input, you'll see a benchmark mode equals 1. So go ahead and delete that. Okay, and then for all 3 of these main input files, set these parameters in the problem size name list and the temporal controls name list.
We just set it to 0 instead of deleting it. Is that the same?
Yeah, I think it's the same. -1 is certainly the same as deleting it. I think 0 is the same too. It's best to delete it because then it defaults to whatever that tells it not to mess with it. So main input Jupiter and main input Sun have a little note about some papers you can look at that if you kind of want to get a sense for what those runs are actually doing. So there are some general physics controls that have nothing to do with your non-dimensionalization or your choice of reference state. This is just like, do I want magnetism on? Do I want this thing rotating? Do I want to have Lorentz forces on? Do I want viscous heating or ohmic heating? So these switches are controlled through the physical controls name list. Okay, and you don't need to set them if you use these values. These are the default values. Okay? So as long as magnetism is on, Lorentz forces will be at work. Viscous heating and viscous heating is always on by default. Ohmic heating is on if magnetism is on. Okay? You can set these by just switching true defaults. Okay. And when magnetism is false, the induction equation isn't solved. None of that goes on. I will say viscous heating right now is off in the Boussinesq mode that we'll discuss. That's going to be fixed soon, but I realized I had an incorrect coefficient in front of that. I need to check. So when you run the benchmarks, ohmic heating is turned off, but its default is to be on. Okay, so we'll just kind of go through this. There's boundary conditions. So you have some choice of your boundary conditions, okay? Basically, no matter what you want, the boundaries have to be impenetrable. Okay, that will never change. I don't know how to address other options there. But the magnetic field right now always matches onto a potential field. Okay, but other options for that are in development. I just don't have them set up right now. That takes care of all of the benchmark runs, and it's useful for various kinds of dynamo studies. But I'm going to move on that probably in another month or so. That's on both boundaries, yes. So what you get to decide about are the thermal and the horizontal flow boundary conditions. So first of all, for the thermal boundary conditions, okay, these are basically the flags that you can set. Okay, and these are the default values that are set. You can modify those as you wish. One thing in the code, throughout the code, I tend to use TVAR, which is like the thermal variable. Okay, but occasionally I have entropy, and occasionally I have T. So whenever you see in something that you set, something like DTDR or TVAR, that can be entropy or temperature. It just depends on whether you're running anelastic or Boussinesq, basically. Okay, and so you can set. Basically, for temperature, you can set either the value or the gradient at either boundary. Okay. And the way you do that are for these flags, fixed TVAR top or fixed DTDR top, or fixed TVAR bottom or DTDR. Sorry, that should be bottom right there.
Me?
Yes.
Can we apply conductivity in the core?
Not right now. Yeah. That's the only magnetic field boundary condition right now, is potential field. And so you don't need to specify all of these. Just pick a pair, one top-bottom pair and one value pair, or pick nothing if you want to, the default is to fix the temperature at the boundaries and to set T-top and T-bottom to 0 and 1. Okay, just a pretty standard kind of Boussinesque setup. And so you can try this if you want, just to see. Try in this Boussinesque case, assigning a temperature contrast of 2 instead of 1. I don't know why you would want to do that in Boussinesque. And then run the code, and we'll kind of build on this as we go. Okay, so let's just try, right? Edit the main input file in your Boussinesque directory. Okay, and we'll just try changing the temperature to 2 at the top. Just verify that you can, make that modification and run the code. I'm sorry, did I say change the temperature at the top? I meant the bottom. Yeah, don't set the temperature at the top to 2 and the bottom to 1. So nothing magic here. So we'll kind of move on, but just make sure you can do that. So just set T-top or T-bottom to be 2. And we'll talk now a little bit about the horizontal flow. Okay? So basically, your horizontal flow conditions can be no slip or stress-free. Again, they're specified in the boundary conditions name list, and I've indicated the defaults here and the relevant flags. You only need to specify one set, and if you set no slip will override stress-free, and then no slip boundaries will set no slip top and no slip bottom simultaneously. Okay, so the default is to have both boundaries stress-free, and then you can play with various combinations of these to reset that. Okay, and so why don't we try it with our Boussinesque example? Let's give it stress-free boundaries now, just to verify that everything seems to work okay.